Hello, welcome to my presentation. I'm Elisabetta de Giovanni and I'm a PhD student in the Embedded Systems Laboratory of EPFL in Switzerland. This work was a collaboration between ESL and the University of Bologna and ETH Zurich. Today I'm going to discuss how to design and optimize biomedical applications in a modular way in ultra-low power heterogeneous platforms. Recent projections of healthcare spending per capita show an increasing trend with an average of 2.7% per year expected by 2030. This is due mostly to population aging and an increased incidence of non-communicable diseases that cause around 71% of global mortality. Within NCDs, cardiovascular diseases are the major cause of death, representing 31% of the global mortality. Considering these two major problems, there is an increasing need of remote, long-term health monitoring to detect, prevent, and even predict NCDs through wearable sensors and automatic biomedical applications, and also, of course, lower the healthcare cost. In the last decades, wearable sensor nodes evolved from single-core, simple platform to ultra-low power devices and multi-core platforms to ensure more accurate and complex diagnostic with minimal energy consumption. In fact, WSN platforms offer many advantages, one of which is parallelization through multiprocessing that can highly reduce energy consumption, power management through clock and power gating to ensure reduction of consumption during inactive time. Then the recent platforms have independent memory banks that can be power gated depending on the needs of the application. And finally, domain-specific accelerators can be used to accelerate intensive computational kernels. One of the recent platforms that offer all these advantages is the open source RISC-V based PULP platform. There are various evolutions of this architecture, but we focus on the multi-core one. The main features of PULP that can be exploited for biomedical applications are a main processor or fabric controller with power management capabilities, an 8-core parallel computing cluster for multiprocessing, and finally a multi-banked L2 memory to implement memory management. However, in order to exploit these features in WSN-based biomedical applications, it is necessary to optimize them properly. For this reason, we conducted an analysis of the impact on the energy savings of attainable speedup and application duty cycle in an 8-core parallelization. As shown in the figure, we ran this analysis on one of the instances of PULP called Mr. Wolf. Additionally, we show the impact of having 8 banks active or 1 bank active. What we can see from the figure is that we need a speedup of at least 4.6 to achieve minimum energy savings. Moreover, in the figure on the right, we can see that for lower duty cycles, higher energy savings can be achieved due to power and memory management, but this is not the case for higher duty cycles, as power and memory management have less impact, while higher attainable speedup is more relevant. So, the output of this analysis is that we need minimum speedups and correct memory management, otherwise we may limit the potential energy savings. But how to properly parallelize and memory optimize WSN-based biomedical applications? A key component to achieve high speedups in WSN-based biomedical applications is modularity of the parallelization. In fact, most of the biomedical applications include typical modules to process the signal and detect events or pathologies. Throughout the presentation, we are going to use an example of an ECG-based application. The first module is a filtering process which removes noise. The morphological filtering is the example we use, which removes uses the shape of the signal to remove baseline wandering and high frequency noise. Then the signal goes through an enhancement process, which can amplify relevant information or combine multiple channels. In fact, we use two techniques, one called relative energy, which amplifies the main wave of the ECG, or R-peak, and the root mean square combination, which combines the ECG leads. Then the third module is the feature extraction module, which extract main characteristics of the signal, and in our case we consider what is called the ECG delineation, which extracts the main wave of the ECG, the R-peak, and the fiducial points, which are the smaller waves. Finally, the last module is the inference module, which can be any kind of classification or even prediction of pathologies or anomalies. And for this we use a well-known heartbeat classification algorithm using random projections. Then the output of the inference can go to a mobile device to alert the person or inform a doctor. In the context of WSN-based biomedical applications, we propose modular software and hardware optimizations to maximize the speed-up and overall reducing energy consumption. First, we describe some application-level optimizations. Then we propose a top-down approach for parallelization per module, which includes data-independent techniques to achieve higher speedups, and then data-dependent and general data level optimizations. These are what we call platform-independent optimizations. Then we also propose platform-aware optimizations, first power and memory management, and then hardware acceleration of intensive computational kernels within the modules. On the right, we show the conceptual architecture that is based on pulp, and we will use throughout the presentation. As first platform-independent optimization, we consider the application level, and we consider an example of ECG heartbeat classification that we mentioned earlier. The original application applies a heartbeat classifier to a single lead ECG to detect if the heartbeat is normal or abnormal. If the heartbeat is abnormal, a second stage of the application is activated, that is a 3-lead ECG delineation, which is more complex. So, considering 46% of the patients analyzed having less than 10% of abnormal beats, the first optimization is that the algorithm runs mostly the first stage of the application. But also, if we consider a multi-core platform, we need to consider the 27% of patients with high occurrence of abnormal beats. And for this, running the 1+2 application is way less convenient than running always the 3 leads delineation. So in this case, and in the case of the rest of the patients, based on a threshold that can be trained to each patient, we can choose between running a full 3 leads delineation, or a single lead, or a 1+2 leads. Then, to maximize speed up in biomedical applications running on multi-core platforms, we propose a top-down approach to modular parallelization, which is implemented in the 8-core cluster of our conceptual architecture. The first type of parallelization to consider is a lead parallelization, which is data independent. In fact, in biomedical applications often happens that multiple leads or channels are acquired, and each lead can be processed by a different core. We use this technique for the 8 leads morphological filtering. However, in a lot of cases, the input signal is a single lead, so this parallelization cannot be applied. In this case, a window parallelization can be implemented. In this case, the data to be processed is divided in multiple windows of the same length, and they are assigned to each core for processing. This can also include an overlap, which shouldn't cause a big overhead. And we use this technique for the relative energy and the R peak detection. Then, in the case of ECG or other cardiovascular-based signals, these are characterized by heartbeats, and in some applications, the same operations are performed for each beat. So each core can be assigned to each heartbeat. This approach has a little overhead due to the physiological differences of each heartbeat, but it doesn't impact highly on the overall results. We apply this to the fiducial point delineation and the beat classifier. Then, if none of these techniques can be applied, a general data level parallelization can be implemented. This can be implemented on any inner kernel of the application. For example, we use it on the RMS combination. Each core receives a similarly sized subset of samples from all the leads, and it computes the RMS for the 3 samples of the 3 leads independently till the subset finishes. The main message of this top-down approach is to consider first the parallelization techniques that are likely to produce higher speedups. The next platform-aware software optimizations include power and memory management. Considering the low duty cycles biomedical applications, power management through clock gating of the fabric controller can achieve high reduction in energy consumption. In fact, in these states, it can consume as little as 12.6 microwatt with full L2 retention in the conceptual architecture we are considering, and as little as 6.6 milliwatts in active mode running at maximum frequency. Then another important optimization is memory scaling and management. We first scale down the memory banks to 16 kilobytes each, since it's the resolution that we need for our applications. Then we propose a strategy of changing the state of the memory during acquisition. For example, if we have 60 seconds of buffer to store, which is roughly 30 kilobytes for an integer 16 bits, the first memory bank is activated. Then once it's full, the next one is activated and the previous one is put in retention mode, and so on till the memory is full or till it's needed. This can of course be scaled to the smallest feasible resolution for the needs of the application, and in fact it is necessary to have platforms with smaller banks and apply power management through clock and power gating both the main processor and the memory. Finally, we apply hardware acceleration for intensive computational kernels, which is done with a two-step process. First, the kernel selection stage uses an execution profile report to select the most intensive kernels. These are usually short kernels due to the limited instruction memory. In our case, we have selected 3 kernels, one in the filtering module, specifically the morphological filtering, which is a linear min-max search, then a linear peak search in the future extraction module, and a circular min-max search in the inference module. Then the second step is the kernel mapping, which is a manual identification of operations to parallelize. To show the results of our analysis, we used the test benches for the biomedical modules extracted from two publicly available databases. One is the PhysioNet QT database, where we extract 4 different cases, average, worst, and best in terms of signal, noise, and shape. And then the MIT arrhythmia database, where we also extract 4 different cases in terms of percentage of abnormal beats. Then, as test benches for the biomedical applications, we used a well-known 3-lead ECG heartbeat classifying application and then a standard 12-lead ECG delineation. These test benches are run in a multi-core WSN platform based on PULP, where we measure the execution time and estimate the energy consumption. The OpenPULP platform provides an SDK where we ran the RTL simulations using Model Sim, which is cycle accurate, and to estimate the energy consumption, we used the values from Mr. Wolf, a multi-core PULP platform instantiated in 40 nanometers TSMC technology, which includes a SOC domain and an 8-core cluster running at the lowest energy point for this platform of 0.8 volts and maximum frequency. Then, for the CGRA, we consider a specific design for biomedical applications that can be connected to the SOC domain or the cluster. The first result that we show is the execution time of the different modules on the single-core versus multi-core design and the multi-core versus the multi-core plus the CGRA. From the figure, we can see that overall the modules achieve a speed up higher than the minimum threshold discussed earlier. Then we can see that the maximum speed up is achieved for data-independent techniques, while lower speedups are achieved in data-dependent modules where the physiological characteristics change the workload through the cores. This is translated directly to the energy consumption estimation, where the multi-core shows high energy savings per module, while the CGRA gives modest benefits, and this is due to the short kernels and the low impact within the module. But overall, the 8-core parallelization with the top-down approach presented and applied to independent modules can achieve up to 60% of energy savings. Then we show the application level energy savings, which include also data acquisition and memory management for the 3 leads and the 12 leads application. The figure shows that the multi-core design highly reduces energy consumption in both applications, but the impact is much higher in the most complex one, or with the higher duty cycle. This translates also to the hardware acceleration impact. In the case of full applications, the ratio between acquisition and computation highly affects the energy savings. Hence, in low duty cycle applications, it is better to have bigger number of banks and scale to the memory to a feasible resolution, since the memory management has a very high impact. Finally, we show the results considering the software and hardware optimizations independently and combined. If only parallelization is applied, we can achieve 41.6% of energy savings for the 12-lead application, while if we apply only the hardware acceleration that can be applied to the single-core platform, we have modest savings. Then we can apply also only power and memory management alone, and this can impact highly in less complex applications like the 1 lead. Then if we apply only software optimizations, which can be used, for example, in commercial platforms, we can achieve up to 46.10% of energy savings. And finally, combining all of the software and hardware optimizations, we can achieve up to 51.3% of energy savings. So, in summary, parallelization, power and memory management, and hardware acceleration can be applied independently and combined to achieve significant energy savings. In conclusion, what we saw is that modern ultra-low power WSNs offer multiple energy saving advantages. One is the multi-core processing with power management, but we need to achieve a minimum speed up to have minimum energy savings. So we proposed a top-down approach for modular software parallelization, where we first consider data-independent techniques to achieve higher speedups, and then second, data-dependent techniques for lower but significant speedups. Then we can have memory management as an orthogonal optimization, achieving additional energy savings up to 23.45%, and also we can add modular hardware acceleration to further increase the savings for a total energy savings up to 51.3% for a standard 12-lead ECG delineation. So this concludes my presentation. Thank you, and for any questions, see you at the live Q&A session.